One of the main goals in the Quaid group is to make chemistry more efficient. Instead of doing traditional synthesis where you have to isolate and purify each product after every step, we're trying to develop systems where you can take all of your reagents and put them in one flask, then perform 2, 3, or 4 reactions in one flask before only having to isolate and purify the final product. One of the approaches we're taking is to encapsulate catalyst, since catalyst incompatibility is one of the big reasons that we're not already doing multiple reactions in one flask. So the way we're trying to do this is to encapsulate a large polymeric catalyst in a polymer shell. And the shell should have pores that are small enough so that the large catalyst can't get out, but still large enough so that the small molecular reagents and products can diffuse in and out. So you can imagine your first reagent diffusing into one capsule, being transformed into the product, diffusing back out and into a second capsule, and so on until you get your final product. An example of this is the encapsulation of a polymeric amine catalyst. We can encapsulate polyethylene imine, or PEI, in a polyurea shell, and then use it for the transformation of an aldehyde to a nitroalkene. This catalyst also adds a second equivalent of nitromethane to the nitroalkene, forming this dinitro product, which isn't a particularly useful product. But if you add a second catalyst, this nickel-based catalyst, and a second reagent, and do the reaction again, you can actually direct the reaction away from this dinitro product and to this Michael adduct, which is actually a precursor to a class of pharmaceutical compounds called GABA analogs. So in doing this tandem catalysis, you not only direct the reaction to get a completely different product, but you can get an 80 or 90% yield for this two-step reaction. I should also point out that this reaction wouldn't be possible if the amine catalysts weren't encapsulated, since the amine and the nickel will chelate, rendering each other inactive. Our second approach involves the use of microreactors. And here we're going from batch to flow, but the overall concept is still the same, where you can introduce 2 reagents up at the top, have them react in the channel, and then add a third reagent a little farther down the line, make it react in a second reaction, and so on until you get your final product out at the end. So again, we're going from batch to flow when we're going to microreactors, but we're still putting all reagents into one reaction vessel and getting a final product out the end. So the overall idea is still the same, whether it's in flow or in batch.